Alright, hey there guys. My name is Wilfrid and I'm a senior math tutor. And today I'll be covering 10 questions surrounding algebra and some mathematics. A little bit backstory upon myself. I graduated from master with a major in biochemistry and a minor in mathematics. And if you have any additional issues with your homework or with your if you encountered any problems that you found tough on your tests or assignments, please submit them through OneClass and we'll try to get to them as soon as possible. So let's begin. Alright, so the first question reads, how do you multiply a 1 by 2 matrix by a 2 by 3 matrix? So in the past, I covered matrix multiplication. So the first thing to know about matrix multiplication is that matrix multiplication is the multiplication of two different matrices. So let's say we have matrix A and matrix B, and the resultant is matrix C. So we don't get a number, we get another matrix. So another rule surrounding the matrix is that some of the dimensions have to be the same. So first of all, let's say, so the property is that the first matrix's number of columns has to be the same as the second matrix's number of rows. Okay, so the convention that we write is let's say that A is a 2 by 3 matrix. So 2 by 3, that means that it has 2 rows times 3 columns. Okay. So if you want to do matrix multiplication, you need to make sure that that you have this formula. So if we have matrix A times B, and matrix A is of the dimensions n by m, then we need to make sure that matrix B is of dimensions m by, and that could be whatever dimension, it could be m by h, okay? And the resultant matrix is matrix C, and it will be n by h, okay? It will produce a matrix that has n rows and h columns, okay? So going to our specific example here, we have a matrix that's a 1 by 2 matrix and a 2 by 3 matrix. So we already know that if we were to label these like this, that this is valid for matrix multiplication. Okay? And the new matrix, the new resulting matrix, will be a 1 by 3 matrix. So there's going to be 1 row and 3 columns. Okay? So how do we think about making this new matrix? Okay, so let's say that our matrix A consists of 1 row and 2 columns. So it's, let's say, integer values A and B. Okay, and we have our matrix B, which is 2 rows and 3 columns. So let's write out our integers here. So there's 2 rows, so C, D, E, and 3 columns. So F, G, and H. Okay. So if we were to multiply these two together, what will we get? So let's do A times B times C, D, E, F, G, H. Okay, so we know we're going to get a 1 by 3 matrix. So let's try to write it out like this. Okay, so if we're going to get a 1 by 3 matrix, we have 1 row and 3 columns. So we'll have 3 values here. So let's do this first value as this red bracket here, the second value with this green bracket, and this third value with this blue bracket. Okay, so that's going to be our 1 by 3 matrix. Okay. Alright, so how we matrix multiply is we're going to take, so the first value is going to be the sum of the products of A times B and B times F. Okay, so this first value here is going to be the sum of the products of the first row and the first column. Okay, so that means that here we get, so the first value of the first row is A times the first value of the first column, which is C. So we're going to get A times C, and we're going to sum that with the second value of the first row plus, or the second value of the first row times the second value of the first column. So that's going to be b times f. Right? So we're going to sum those together to get our first value of our new resultant matrix. All right, let's talk about the second value. So now we're going to consider this first row again with the second column. Okay? So whenever you're matrix multiplying, you can think about it as the first matrix, you're going to multiply the values of the rows to the second matrix sees the values of the columns. And the position of the columns or the rows is determined by where you are in this resultant matrix. Okay, so we're going to take the first value of our first row in our first matrix, which is A, times the first value of our second column in our second matrix, B. Right? So that's A times D plus the second value of our first row in our first matrix, which is B, times the second value of our second column in our matrix B. So that's going to be B times G. Okay? Finally, we're going to write out this last one. I'm not going to really explain it, but if you want, you can pause the video and you can try it yourself. It's going to be A times E plus B times H. And that's our new resultant matrix, okay? A 1×3 matrix. So another thing to note is that this is not commutative, okay? And what commutative means is that in I guess, simple multiplication with, I guess, numbers. So let's just write out this. So commutative means that 2 times 3 equals 6, but we can also write it as 3 times 2. In matrix multiplication, you can't do this commutative property where you can reverse the values unless there are square matrices. Because let's say that we have this example here. So it's a 1×2 times a 2×3. If we were to do A times B equals C, that is not the same as B times A because now we reversed it, right? So this is a 1×3 times a 2×3 times a 1×2. So you see here that the number of columns in the first matrix is not the same as the number of rows in the second matrix. So now we can't make this multiplication occur. So this is a commutative property, okay? So the junior tutor provides us with a solution to make it more tangible for us to understand. So we're going to do the solution really quickly, okay? So let's say that A equals 1, 2, like this, and B is 1, 0, 2, 3, 5, 4, and they want us to find what A times B is. So A times B is going to be this, right? So we already know that this is going to be a valid multiplication because we know that there's the same number of columns to the same number of rows. So we're just going to do this, okay? So the first column in our new resultant matrix is going to be 1 times 1 plus 2 times 3, which is 7. The second value is going to be 1 times 0, which is 0, plus 2 times 5, which is 10. And the final value is going to be 1 times 2, which is 2, and 2 times 4, which is 8. 8 plus 2 is 10. So our new resultant matrix is a 1×3 matrix with the values 7, 10, and 10. Okay, so this is how you matrix multiply, and this is how you matrix multiply in general. So when you get to a larger matrix, you're going to need to do a lot more multiplication and adding together. So this was a more simple example. So this solution and explanation is correct. Nice job. Cool. All right, let's move on to the next question. All right, so the next question is kind of long here, and it reads, so it's kind of a fill in the blank first, and then they give us an example to solve. So the fill in the blank reads, to solve a polynomial inequality, we factor the polynomial into irreducible factors and find all the real blank of the polynomial. Then we find the intervals determined by the real blanks and use the test points in each interval to find the sign of the polynomial on that interval. So let the polynomial be p of x equals x times x plus 2 times x minus 1, and fill in the diagram below to find the intervals on which p of x is greater or equal to 0. So what is this really asking us to do? Okay, so first of all, we need to determine what a polynomial identity is, okay? So they gave us a polynomial p of x equals x times x plus 2 times x minus 1. Okay? So the polynomial inequality, like any other inequality, sets this polynomial to be greater than or equal to some kind of number. So in this case, our polynomial inequality reads that this has to be greater or equal to 0. Okay, so we need to find all the values of x that will make this value greater or equal to 0. Okay, so this is going to take us a while because there could be a lot of different values of x that will make this equation true. So we're going to go work through this systematically, and we're going to have to determine the zeros. And I'll get into why we need to determine the zeros in the first place. Okay, so let's draw a number line here, okay? Actually, let's just draw a positive and negative, okay? So this is our x and y axis, okay? We don't really care about the y too much, but I'm just going to put positive y, negative y, all right? And positive x, negative x, okay? So the zeros of a polynomial are the solutions to the equation when this polynomial is equal to 0, right? So it's the values of x that makes this polynomial equal to 0, okay? So I'm not going to graph it out per se. I'm just going to use a different example. So let's say that we have polynomial of a different polynomial. So it's like f of x, okay? And we know that this is going to be a polynomial, okay? And let's set f of x to be equal to x squared. So we know that this is going to be a parabola. Maybe we should do x squared minus 1. Okay, so we'll set x squared minus 1. So if it's x squared minus 1, then we have this. This is our polynomial right here, okay? So here we have a third degree, but we're going to use a second degree, okay? And I'm going to describe why the zeros are very important in this case. So the zeros help us to determine where the polynomial is equal to 0. So the zeros are here and here, which is positive 1 and negative 1, okay? So these are the only values in the entire polynomial, in the entire function itself, which will equal to 0. And this helps us to find the parts of the polynomial which will be positive and the parts of the polynomial which will be negative. Because if we are guaranteed that these are the only values that are equal to 0, then the values in between the zeros are going to be of 1, are going to be negative, and the values outside of that interval is going to be positive only. So you see here on our example here that the values between our zeros of 1 and negative 1 are all negative, right? If there was another 0 here, for example, then it might switch to positive and back to negative, right? But we know for a fact that the values between our zeros are either going to be all negative or all positive. So you see here past 1, it's positive, and past negative 1, it's positive. So when we're filling in this blank, right? So to solve a polynomial inequality, we factor the polynomial into irreducible factors. And find all the real roots or zeros of the polynomial. So we're doing what we usually do with a quadratic equation, with a polynomial equation. We find the zeros of our polynomial. And by doing so, we can use these zeros to define intervals in which we can determine whether the polynomial is positive or negative within those intervals. Okay? So let's use the example that the question proposes, okay? And also I'm going to use this diagram that they use, I guess, too. So, given our polynomial of p of x equals x, x plus 2, and x minus 1, we have 3 zeros here, okay? So I'm going to draw a number line here again. Okay, so this is infinity, and this is negative infinity, okay? So we'll have our first 0 of negative 2, our second 0 of 0, and our third 0 of 1. Okay, these are not drawn to scale, but we know for a fact that based on our polynomial, which is already factored irreducibly, we have zeros of 0, negative 2, and 1. Okay, so now we're going to use test points within these intervals that are defined by our zeros to figure out whether our polynomial in this interval here is positive or negative, and whether our a polynomial is positive or negative in this interval and this interval. So we have 4 intervals we need to check. So we have this interval, which is negative infinity to negative 2. we have this interval, which is -2 to 0. We have this interval here, which is 0 to 1. And we have this interval here, which is 1 to infinity. Okay? Cool? Cool. So we're going to gather test points from each of these intervals, and we're going to sub them into our polynomial and see if it comes out negative or positive. Okay? Alright, so let's test out our first interval here, which is -infinity and -2. Okay, let's use our test point of -3. Okay, so if we were to write p of -3, what do we get here? We get -3 times -3 plus 2 and -3 minus 1. Okay, is that right? Is that our polynomial, by the way? Yeah. Okay, so what do we get here? So we get -3 times -5 times -4. So we have negative, 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 -15 times negative. So 15 times -4 is 60. Oh, whoops, 60. So it's -60. Okay? So given our principle that every value in between the intervals of our zeros has to be of a negative value or positive value, we can then conclude that in this interval of -infinity to -2, all the values of our polynomial are negative, given this test point. Okay, let's do our next test point here. Let's do -2 and to 0. Okay. Let's use a test point of -1 because that's in between each. So we have -1 times -1 plus 2 times -1 minus 1. And that gives us -1, 1 minus 2. And that gives us negative times positive is negative, times negative is positive, so we get 2. So now we have determined that in between this interval, p of x is greater or equal to 0. In this interval here, we know that p of x is less than 0. Okay, let's move on to our third interval here, which is 0 and 1. Okay, so we'll test out p of 1 over half. So that's 1 over half minus half plus 2 minus half minus 1. Okay, what do we get here? We get 1 over half times 3 over 2 minus 3 over 2. Okay, so this is going to be negative, negative, positive, negative, so it's going to be 1, -1. Yeah. Let me just check my math here. 4, 8, that's not right. That's going to be -9 over 8. Man, my math is bad. Okay, so we know that in this interval here, our polynomial is always going to be negative, so less than 0. And finally, let's test our last interval here, which is 1 and infinity. So we're going to use 2, for example. So p of 2 is equal to 2 minus 2 plus 2. Hold up, sorry. That's 2 plus 2. I don't know why I wrote a half here. This should not be negative there. This is 2 plus 2. And it's going to be 2 minus 1. I don't know why I wrote halves here. That's that's my mistake. I'll change this after I finish this. So it's 2 times 4, 8 times 1, which is 8. Okay, so we know that p of x is greater or equal to 0. Okay, let me just change this for real quick here. So this shouldn't be negative. That shouldn't be negative over there. Okay, so what do we get here? This is actually 5 over 2. So So this is 5 over 2, and this is going to be negative half, right? And so that's going to be negative 5 over 8. Sorry about that. I don't know why I wrote negative half there. Okay, so cool. So we've tested all these intervals out, and we found our solutions, okay? So let's just write down our final solution here. Therefore, in intervals negative 2 to 0 and 1 to infinity, p of x is greater than 0. Okay, cool. So that's how you solve this this question here. We first of all found the irreducible factors because they were given to us. We found the zeros. We reasoned that the values between the zeros will always be negative or positive. So then with that reasoning in mind, we tested each of these intervals by making a test value and seeing what the value of our polynomial is. And by doing so, we found the intervals that our polynomial is positive or greater than 0. So there are other ways to really do this. You can use derivatives. You can also reason with the nature of polynomials that the intervals and the regions actually interchange. So it goes from negative to positive to negative to positive, and there's zeros. There's a ton of ways to do this. You can even graph it visually and just look at where it is positive. But overall, we use this method of test points and intervals to find our positive values of our polynomial. So this solution is correct. Good work. Cool. All right, let's move on to the next question. All right, so what is the domain and range of y equals ln x? So the domain is defined as all values of x where f of x is defined. So where all values of x is defined. So what that means that it doesn't go to infinity, it doesn't make a undefined number, it doesn't make a complex number, I guess. So that's what a domain is. That's all the valid values of x where f of x is defined. Okay, so the range of a function is all values of f of x that are mapped to x. Okay, so if we were to think about it, here's our pool of x values that are valid. So our function, let's say f, takes our domain values and plugs it into our range values. So this is our range, and this is our domain. Okay. So a neat thing about this is that the f of inverse helps to reverse this. So now if we use f of inverse, this becomes the domain of f of inverse, and this becomes the range of f of inverse. Okay. So one way that we can find the range of our function is to find the inverse function and find its domain, because the domain of our inverse function is equivalent to the range of our actual function. And we're going to use this technique to find the range of our function y equals ln x. Okay, so let's do this specific example. So the nature of y equals ln x, so when we're talking about this domain, is that all the values of x that make f of x defined are y defined. Okay, so the natural property of a logarithm is that the argument within the logarithm itself has to be positive. And this is the nature of the base, and how the base can never be converted to a negative number. Okay, so especially since our base is a positive number here, another way to write y equals ln x is by writing e to the power of y equals x. So we know that y will always need to be x needs to always be positive, because e can never be is a positive number, and any positive number to any power will always output a positive number. Okay, so we know, and we reason by the nature of our function, that x always has to be greater than 0. Okay, it has to be a positive number. Okay. So what about our range? Okay. I'm going to write the domain as this too. Okay. So what about our range? Okay, so we're going to take the inverse function, which I already made here. So y inverse is actually, if we apply e to both sides, is e to the power of y equals x. Okay, so what is the domain of this function here? Well, the domain of this function is that x can be any, or y can be any of the real numbers. Okay, so x belongs to the real number set, or sorry, y belongs to the real number set. Okay, so y belongs to the real number set. Therefore, if we were to transform this back to our actual function here, the range, according to our principle here, will be that y belongs to the real number set. Okay, it could be negative infinity, it could be positive infinity. So that means that it's from negative infinity to positive infinity. All right, and we solve the range by finding the domain of this inverse function, right? So we notice that y can be any number, negative, positive, decimals, it can be anything, right? And because of that, we found the domain. When we switched it back to the actual function, the range is also the same as the domain, right? So I guess another way you guys can do this is that you can graph this function and you can visually identify what the domain is, right? And you can visually identify what the range is. But this is another way of doing it without graphing it out. And we use a lot of reason and this principle of f inverse to find our range and domain. So this solution is correct. Okay. All right. How do you graph the equation negative x plus 3y equal 9? So whenever you're graphing any kind of function, first of all, you have to identify what kind of function it is. Okay, so we look at our equation here, and we see here that you know, there's no powers, there's no squareds, there's no cubic powers, right? So we now know that this is a line equation. Okay, so this line equation basically satisfies saying what are the values of x and y that will equal 9. So it's going to be a line, essentially. So usually when you're trying to graph a line, you need 2 points of that line. So what we can do is we can find the x-intercept of this equation and the y-intercept of this equation. And by doing so, we can plot them on our graph here, and we can find our line. Okay, so let me first label our axis here. Okay, so let's write out our equation again. So negative x plus 3y equals 9. So let's just try to be simple here. We're going to try to find our x-intercept and our y-intercept. So our y-intercept is the point on the line which intercepts the y-axis. And another point about that is that the y-intercept has an x-coordinate of 0. Okay? And we're also going to find our x-intercept. The x-intercept is the point of the line where it intercepts the x-axis. And another property of x-intercept is that the y value, or the y-coordinate of the x-intercept, is equal to 0. So let's first find the y-intercept, okay? So y-intercept, we set x to be equal to 0. Okay, so what do we get? 0 plus 3y equal 9. If we isolate for y, we get 3. Right, so our x-intercept is 0 and 3. Cool. What's our x-intercept? Okay, so x-intercept. So we're going to set y to equal to 0. And what do we get? So we got negative x plus 0 equals 9. And we get x equals negative 9. And so we have negative 9 and 0. So let's plot this out onto our graph here. Okay, so 0 and 3. So if we were to have 0 and 3, it would be like here. So this is 0 and 3. And negative 9 and 0. So let's just say it's like all the way over here. Okay, cool. So now we can graph our line, which we're going to just connect these two coordinates. So excuse me while I try to draw a straight line. All right, close enough. All right, we want to draw a line through this because it's our line equation. All right, so this is our line equation, and we just graphed the equation by finding the two intercepts. Now you can find different points on the line. So for example, you can plug in 1 and see where that is, and you can plug it here. And you can plug in some other value, and you can plug it there. But I find that using the x-intercept and y-intercept helps us to graph it correctly and appropriately. So yeah, this is how you graph the equation. And these are all the pairs of x and y that satisfy this equation. So yeah, so this is the graph. The junior tutor also did the same thing. They found x-intercept and the y-intercept, and they graphed our equation. So this solution and graph are correct. Okay. All right, question number 5. So how do you factor 3x squared plus 5x plus 2? So I covered this question pretty extensively in the past, and I used the cross multiplication method, and I'll go through it again. So when they when they ask us to factor 3x squared plus 5x plus 2, so let's say that we have our standard form of our quadratic function here. So it's ax squared plus bx plus c, right? When they want us to factor it, right? So if they want us to factor, let me use a different color line here. So factor means that we want to reduce it to this form, okay? And this form is coefficient dx minus, it could be plus or minus e times fx plus or minus g, where d, e, f, g are all coefficients, okay? And so there's a rule about these coefficients, okay? And the rule is that A, B, and C equal a certain combination of these coefficients, okay? So A equals, or A is equals to D times F. C is equal to E times G, and B is equal to the sum of these two products. So D times F plus E times G. Okay, so this is basically the cross multiplication rule, or this is how I like to describe it. And this is a more, I guess, general format of how to describe it. Okay, so A is broken down to its factors of D and F. C is broken down to its factors of E and G. And B is the sum of the factors D times F plus E times G. All right. So we need to find a certain factors of A and a certain factors of C so that we get our middle coefficient of B. Okay. So let's go to our general example here. All right. So we have 3x squared plus 5x plus 2. Okay, so let's think about the factors of 3x squared, right? Obviously, there's an x. So to make positive 3, we can either have negative 3 times negative 1 or 3 times 1, right? So if we were to break this down, we have two different pairs, right? I'm going to write down all the pairs today. So we have negative 1 times negative 3 or 3 times 1. Okay. So let's think about the factors for 2. So the same way, we can have the negative pair, which is negative 1 times negative 2, or 2 times 1, right? So we need to pick a certain combination of these 4 factors, or pairs of factors, to get our middle coefficient, okay? So let's test out negative 1 and negative 3, and 2 and 1, okay? Let's test this out. So let's write out here test. So we have negative 1 and negative 3 as our first pair, and we have 2 and 1 as our second pair. Okay? So where cross multiplication comes in is we're going to cross multiply and add these together. So we're going to have -6 here plus -1, which is -7. So that's a no-go, right? We see here that that doesn't equal the middle coefficient. So another thing we can do is we can switch up the order of these pairs. So let's say test number 2. We're going to switch up -3 and -1 and 2 and 1. Okay, so we're going to cross multiply these. So we have -3 and plus -2, which equals to -5. We're very close, right? It's a negative number, but it's the right magnitude, right? It's the right number, but it's just negative, right? So now we need to rethink this, right? So we have the correct ordering, right? But we might not have the right pair. So let's say, okay, let's test 3. Let's choose instead 3 and 1 and do the same ordering, okay? So test 3. We're going to write 3 and 1 here and 2 and 1. So we're going to cross multiply, bam and bam, and we get 3 plus 2 equals to 5. Nice. We have found our middle coefficient and we have found our factors, which is this and this. And now we can write it out, now that we have found the factors, as 3x plus 2 and x plus 1 as our irreducible factors of our quadratic function. So it took me 3 tests to do this, but as you guys keep doing practice and you guys continue to remember your factors and how to order them, you guys can do this in a breeze, and once you see this, you can say, oh, 3 and 1, 2 and 1, okay, those are the factors, and we write out the factors. So it just takes a lot of practice to get used to and mastering the cross multiplication method. But that's how you factor, and this is what the junior tutor did. This is a very nice and elegant example and description, so, and the solution is correct, so this is good. The solution and description actually is correct. Cool. Alright, let's move on to question number 6. Alright, question number 6 reads, what values of b satisfies the equation 3 times 2b plus 3 equals 36? Okay, so this is a classic isolation question where we're going to isolate for our variable b and solve for it. Okay, so we're going to solve for the value of b, which will make this equation true. And I'll bring these guys step by step, okay? So we have our initial equation, which is 3 times 2b plus 3 equals 36. So what I mean by isolating is that we're going to get rid of all of these constants and all these, I guess, numbers, and just have b on one side and all the numbers on the other side. Okay? So due to the nature of the equation, right, so we can say, oh, let's divide both sides by 3. So 2b plus 3 divided by 3 is just 1. So this is, let me just write this all out here, equals 36 divided by 3. Okay, so we get 2b plus 3 equals to 12. Okay, so this equation is still true. We just got rid of the 3. Okay, now we're going to get rid of this negative, this 3 in here. So we're going to subtract both sides by 3. So 2b plus 3 minus 3 equals 12 minus 3. And that equals to 2b equals to 9. Finally, we want to get rid of this 2, so we're going to divide both sides by 2. So 2b divided by 2 equals 9 divided by 2. And what do you know? We get 9 over 2. So supposedly, this is the value of b, which will satisfy our initial equation. So how do we check? We're going to sub this back into our original equation. So sub 1 into equation. Okay, so let's do that. So we have 3 times 2 times 9 over 2 plus 3 equals to 36. Okay, so what do we get? We get 3 times 9 plus 3 equals 36. And that equals to 3 times 12 equals 36. And we know that our left side, hand side, and our right hand side equal the same. Therefore, b equals 9 over 2. Okay, so that's how you find the value of b by isolating, and this is how you check. Check. All right, cool. So the junior tutor didn't simplify it, but that's okay. This is still correct, and the solution is correct. Good work. All right, moving on to question number 7. All right, so question number 7 reads, what is the quotient of x cubed plus x squared minus x minus 1 divided by x minus 1? Okay, so we're going to be using 2 different methods. So the junior tutor uses synthetic division to find the answer, and I'm going to use long division to find the answer. I'm going to go through both with you guys today. Okay, so long division and synthetic division both try to do the same thing. It essentially tries to figure out whether or not a possible factor of a polynomial is actually a factor. So when we look at this quotient x cubed plus x squared minus x minus 1 divided by x minus 1, this question is basically reading, is x minus 1, so another way to write this is x minus 1 a factor of x cubed plus x squared minus x minus 1. So that's another way to read this question. Okay, so how do we know if x minus 1 is a factor of our polynomial here? Well, as with regular numbers, if a divisor is a factor of the dividend, the quotient will not have a remainder, right? So for example, if we were to divide 63 by 7, we know that 7 is a factor because there is no remainder, right? There's no fraction involved. In the same way, we can do long division or synthetic division and determine whether a factor is actually, this possible factor is a factor by seeing that there is no remainder. If there is a remainder, then we have to go back to the books and try to find another factor. Okay, so I'm going to go through long division first, and I'll go through synthetic division. I'll go through how to do each of those, and then you guys can choose which method you find to be more intuitive for you guys, okay? All right, so let's do long division first. All right, so long division, we're going to write out this huge division bracket here. We're going to put our polynomial in here. Okay, x cubed plus x squared minus x minus 1. Okay, and we're going to write our possible factor, which is x minus 1 here. So we're going to try to reduce our number by multiplying our dividend, or divisor, by a certain factor. Okay, so we want to get rid of x cubed plus x squared, right? We don't want that in our actual quotient, right? So what can we do to our divisor to try to get rid of that? We can multiply this by x, okay, or x squared. So I'm going to write x squared here. So x squared times x minus 1, if we expand, we're going to get x cubed minus x squared. Okay, we're going to subtract like in regular division, and we're going to get 2x squared. Okay. So you kind of see how there's a semblance of division here, right? We multiplied our divisor by a factor, and we're trying to reduce our dividend. Okay? So we're going to move our next term down here. So minus x. So what factor here can we multiply to get rid of this number here, or this factor? So we're going to say x, right? So let's do plus 2x. All right, so if we do plus 2x, we get 2x squared, right? If we expand here, times negative 1, so it's minus 2x. And if we subtract, we get x minus 1, or just x, sorry. Getting ahead of myself. And let's carry down our last term here, which is minus 1. All right, so how do we get rid of this x minus 1? We're just going to multiply our factor, our divisor, by 1. And this is what we get, x minus 1. And if we subtract, lo and behold, we get a remainder of 0. So now we know the quotient is going to be x squared plus 2x plus 1. All right, so let's do synthetic division, or what the junior tutor did, okay? So synthetic division. So instead of writing our polynomial, we're going to write upside down. Sorry, let me write down a bigger bracket here. An upside down bracket, division bracket, and we're going to write the coefficients of our divisor, or our dividend. Okay, so our coefficients are 1, right? So the coefficient of x cubed is 1. Coefficient of x squared is 1. The coefficient of x, or negative x, is negative 1. And the coefficient of negative 1 is negative 1. Okay, and now we're going to think about the solution, or the 0. Okay, so instead of thinking about the factor, we are going to think about its 0, right? So if x minus 1 is a factor of this, then the 0, or the solution to this polynomial, is going to be 1, right? Because that's what makes this to be equal to 0, right? So how synthetic division works is we're going to carry down our first term. So we're going to carry it down here. Alright, sorry, give me a sec. We're going to carry it down here. And we're going to multiply our factor to this carry down and subtract it to this factor, or add it to this factor, okay? So if we do that, so 1 times 1, so I'm going to do the arrow here just to show you guys. 1 times 1 is equal to 1, and we add that, plus 1, right? So this is going to be 2. So now we're going to carry this down, so 1 times 2. So let's do another, I would draw another arrow. It might get a little bit messy here. So 1 times 2, we're going to carry it over to our next one, plus 2. So that's going to be 1. And finally, we're going to carry down our last one. So 1 times 1. Sorry, let me just carry it over here. Oh my gosh, this is kind of messy. So 1 times 1. So plus 1 minus 1 equals 0. Okay, so what does this mean, right? So if you have a 0 at the end of your synthetic division, that means that you have no remainder, right? And if you have no remainder, then you know that x minus 1 is a factor of x cubed plus x squared minus x minus 1, or the quotient is going to be, so if this is the x cubed position, and this is the x squared, and this is the x, and this is just the constant, then this is going to be, since you're dividing it by a factor, this is going to be x squared, x, c, and this is going to be your remainder, right? So the remainder is 0. So whenever you're thinking about synthetic division, your quotient at the end is going to be 1 degree of power lower. So if this is x to the power 4, this is going to be x to the power 3. So if we're going to apply these coefficients now, it's going to be x squared plus 2x plus 1. No remainder. So these are the quotients of this division. And I've shown you guys 2 different examples of long division and synthetic division, okay? And we got the right answer. So this solution is correct. Good work. All right, let's move on to question number 8. All right, so the question reads, if y times x equals 144, x plus y equals 30, and x is always greater than y, what is the value of x minus y? So we're given 3 pieces of information. First of all, we're given that y times x equals 144. In another way, we can interpret this as y is inversely proportional to x in this manner. Okay? Next, we're given an example of what x plus y is, which is equal to 30. And our third is that x is always greater than y. So we're going to label these together. So 1, 2, and 3. And we're going to use these 3 pieces of example to find out what x minus y is. So we want to find out what x minus y is equal to. Okay? So first of all, we're going to use 2, and we're going to isolate for y. Okay, so if we take down 2, so let me use a black marker here. So x plus y equals 30. Let's isolate for y. So that's going to be 30 minus x. We're going to sub in 1 here. Oh, sorry. We're going to sub in 1. Actually, hold up. Let me do this the other way. Okay, so we have y and x times x equals 144. What we're going to do is we're going to isolate for x here. So x equals 30 minus y, right? So we're going to sub in 2 here. So sub 2 in, and we get 30 minus y times y equals 144. Okay, so if we expand this, we get y squared minus negative y squared plus 30y equals 144. And if we were to rewrite this, then we get y squared minus 30y plus 144 equals to 0. Okay. So now we're going to factor this. So the factors for this are 26 and 4, I believe. So it's going to be y minus 26 and y minus 4. So we have found two values of y which make these two equations equal to each other. So we're trying to solve for y right now. So y equals 26 or y equals 4. Right? But we still have our third condition, right? So we need to test our third condition here. So if we test our third condition, we know that, so we need to find the values of x first too, right? So sub y equals 26 into 2. So what do we get? So x equals 30 minus 26, which equals to 4. And if we sub y equals to 4 into 2, we get x equals 30 minus 4 equals 26. Okay? So we see here that according to our x is always greater than y condition, our values for x and y, x equals 26 and y equals 4. So we see here that in this first condition here, y was greater than x. So this can't happen due to our restraint on our third condition. So now that we have our x and y, this is very easy to solve. X minus y is also equal to 26 minus 4, which equal to 22. So we have found x minus y, which is equal to 22. Why is this 24? Oh, sorry, y equals 6 here. It's 24 and 26, sorry. Man, my factoring is so bad. Sorry about that. So the factors here are actually 24 and 6. Not 26 and 4. So actually, this should be 6, this should be 6, this should be 24, and this should be 24, and this should be 6. Okay, so then this should be 18. Okay, sorry about that. So that's the answer to our x minus y given these three constraints. Okay, so this solution is correct. Cool. All right, moving along to question number 9. Okay. All right, great. So next question reads, a quadratic equation has a discriminant of 12. Which could be the equation? So the discriminant helps us is a, I guess, formula which helps us to determine the amount of zeros that a quadratic function has. And the discriminant can be written out like this. So discriminant d is equal to b squared minus 4ac. So in this question, they tell us that the discriminant is equal to 12. So they want us to look at each of these options and evaluate which of these discriminants apply to which of these equations. So easy enough, we just need to do a lot of calculations here. So the first one is negative x squared plus 8x plus 2. So our coefficients are negative 1, 8, and 2. So our discriminant here is going to be 8 squared minus 4 times negative 1 times 2. And that's equal to 64 plus 8, which equals to 72. So that's not our discriminant that applies here. What about number 2? So 2x squared plus 6x plus 3 equals 0. A, B, and C, A is equal to 2, B is equal to 6, C is equal to 3. So that's going to be 6 squared minus 4 times 2 times 3, which equals to 36 minus 8 times 3, 24, which is equal to 12. Okay. Our third one is going to be negative x squared plus 4x plus 1 equal to 0. A equals negative 1, B equals 4, C equals to 1. So that's going to be 4 squared minus 4 times negative 1 times 1, which gives us 16 minus plus 4, which is equal to 20. Okay, so that's not equal to our discriminant. And our fourth option is going to be 4x squared plus 2x plus 1 equal to 0. And so b is equal to 2, so it's 2 squared minus 4 times a, which is 4, times c, which is 1. And that gives us 4 minus 16, which is equal to negative 12. We have found our answer, which is option number B, or option number 2. Okay, so calculating the discriminant is an easy way of determining how many zeros our quadratic function has. So if d is greater than 0, there's 2 zeros. If d is equal to 0, there is 1 0. And if d is less than 0, there is 0 zeros. There are no zeros. Okay, and this question basically asked us to calculate the discriminant of each of these quadratic formulas or functions and find which one corresponds to the discriminant of 12, which is option number B. So this solution is correct. Cool. All right, finally, we'll move on to our last question of the day, which is how do you find the vertex of a parabola? So while my question is loading here, I'll continue on. So the vertex of a parabola, like I've taught in the past, is the maximum or minimum value of a parabola. So a parabola can have two orientations. The first orientation is orienting downwards, like this. And in this case, the vertex here will be a maximum. The other orientation, if it's facing upwards, and the vertex in this sense is going to be the minimum. So the vertex equals min, and the vertex equals max. So one way that you can find the vertex of your parabola is by graphing it and visually finding your maximum and minimum values on your parabolas. So another way is by using the coefficients of your quadratic equation or function to use a formula to find the x-coordinate of the vertex and plugging that back in. So let's say that you had your quadratic function of ax squared plus bx plus c, right? And that is equal to y, okay? So the first step is to use the this formula. So the x-coordinate for the vertex corresponds to the division of the coefficient, negative coefficient b, divided by 2 times the coefficient of a. So you can find the x-coordinate of the vertex by calculating this formula. So the second part of it is to plug it in your x vertex coordinate back into your equation to find f of x vertex. Okay? And once you have that, you have found your vertex. So your vertex is going to be x vertex, y vertex. Okay? So let's take an example from our previous question and let's use that. So let's use negative x squared plus 4x plus 1. Okay? So we have negative x squared plus 4x plus 1. Okay, so x vertex is going to be negative b divided by 2a, or negative 8 divided by negative 2, which is equal to 4. So now we're going to plug y of 4 into our equation here. So that's going to be negative 16 plus 16 plus 1. Okay, so that equals 1. So our vertex is 4 and 1. Okay? So last thing to note about vertices, I guess, is that a parabola always only has one vertex. Okay? Only has one maximum or one minimum. Okay? So this general solution is correct. Good work. Cool. All right, so that wraps up today's lesson. I covered 10 questions surrounding algebra and mathematics. If you have any other questions or any other problems, please submit them through OneClass and we'll try to get them to them as soon as possible. Thank you so much for listening, and I wish you guys a good night. Bye, guys.